Good morning. Hello, my name is Phil Smart. I'm the Assistant Policy Manager with the Rail Freight Group. A very warm welcome to the second in our series of 4 technical talk webinars featuring Ralph Goldney of the Rail Freight Consulting, who will be joined by guest speakers from the rail industry. If you missed the first of these, held on February the 7th, on the subject of wagon design, the good news is that it has been recorded on YouTube and can be found by contacting us via the website. This webinar will also be recorded and available later. This week, we focus on the traction power needed to haul our wagons and look at how a locomotive works. So whether you've had a lifetime in the industry and are looking to refresh your knowledge, or if like me, you spent a misspent youth learning the formula for the tractive effort of a steam locomotive but haven't been paying much attention since, then we hope you'll enjoy the next hour or so. If you have any questions, please put them in the Q&A as they occur to you, and we'll try and get in as many as possible towards the end. So it's my pleasure to hand you over to Ralph Goldney, MD of Rail Freight Consulting, who is joined this week by Bob Tiller of GB Rail Freight and Dr. Neil Grennan-Haven. So over to you now, Ralph.
Thanks, Phil. Yvonne, should we start or are people still joining? I'm not in a position to see.
I think people will continue to join. I think we should just start.
Just start.
Yeah.
Okay. Yeah. Okay. Thank you. Well, welcome everybody. Thanks for coming along. I hope you find this enjoyable. You may say, well, why has Ralph got that photo of a tatty old locomotive in the front? And actually, I should say it's not a tatty old locomotive. And Bob Tiller, one of our speakers, has just fessed up to knowing this vehicle very, very well. Worked on saving it, but actually it's because it's a Class 35 Hymic locomotive with a hydraulic transmission system. And we're going to come to this and cover it as we go through our talk today. So we're going to try to give you a description of how locomotives work, how power is generated and transferred to the rail. And then we're going to actually see what happens to that in reality and how Network Rail use that through their freight trailing loads book, so that how the tractive effort is transferred into the maximum train length that can go on a network. So Bob Tiller, previously engineering director, or still at GB Rail Freight, from GB Rail Freight, is going to talk to us about how locomotives work. And Dr. Neil Grennan-Haven is going to talk to us about the basis of the freight trailing loads book with Network Rail and the locomotive lengths that are in that. So with no further ado, I think we'll make a start, shall we, Bob? I'll give you your first slide, shall I? Talk about
Thank you very much.
Work.
Thank you very much, Ralph. Good morning, everyone. So there are several types of locomotives that run on British Railways, but there are several main types, specifically diesel electric. So a diesel engine powering a generator. This generator, as the diagram shows on this exploded diagram of Kestrel, which was built in the 1960s by Brush Traction. This engine is bolted to a generator. The generator then goes through a set of very early electronics in this particular case, but something that we called field diverts. And this is a way of controlling the load from the load behind the locomotive to the railhead and to the engine, so that when the driver powers up, the load is taken evenly, the engine fires, the engine powers up, generator produces amps, and the locomotive pulls away. It's generally a very, very good system. And over the years, many locomotives, 47s, 31s, and 37s have all been powered exactly as we've seen here. The main difference in modern diesel electric locomotives is that they're AC, not DC. These locomotives with DC current, they have DC traction motors. The traction motor is coupled to the axle. In an AC locomotive, they have an alternator, not a generator. And that AC has a much better torque effect on the axle. The effect of the AC current allows a greater torque to the railhead and a better controlling of the load. That way that a lower powered locomotive can be much more powerful than an older DC generated locomotive.
So Bob, here you've got an engine which drives an alternator in this case rather than a generator, and then from there there's a power cable which goes to the traction motors, which are on the axles of the locomotive.
That's correct, yes.
As opposed to your car, for instance, which would have what we call a mechanical transmission, where you've got an engine in the gearbox at the front, and then you've got a shaft that runs down the vehicle, and there's actually a physical metallic gear connection.
That's correct. The only physical connection is a set of wires.
Yeah, so there's a physical connection from the generator stroke alternator to the engine, but from the alternator, basically there's cabling that goes through to the wires. So
there is, and it's all controlled by electronic load demand module.
Yeah, and that's why we call it a diesel electric, because you've got a diesel engine powering electric traction motors. Is that correct?
That's correct. So you've got a diesel engine with either a DC generator or an AC alternator.
Okay.
So if you go to the next slide, Ralph.
Yeah.
So this shows what we call a axle hung traction motor. And this is a traction motor which is connected via a gear casing, which is on the right hand side, to the axle. Now, this is quite an old particular nose hung axle and traction motor assembly. The newer ones, which is an AC, actually have a coupling directly from the alternator to a gear wheel attached to the back of the wheel, and it's much more modern. And they also have inbuilt discs. So we've moved quite a long way from here, but this is actually, majority of locos in the world were actually started like this.
And so, Bob, this is the traction motor here.
That's the traction motor there. So that's a DC traction motor, so it's quite big. AC traction motors tend to be a bit smaller and more directly coupled.
And so these big fat old cables here are coming from the generator. They're the power input, are they?
They're coming from the main traction cubicle, what we call the high tension cubicle.
Yeah. Is this a 66? I think probably is it?
No, I don't think it is, but
okay.
Yeah.
So and so the traction motor is just is what, a couple of steel copper coils, is it?
Just a normal motor that a normal DC motor, just in much bigger scale, and it's capable of very high current.
And so you've got two copper coils, one on the outside and one on the inside.
An armature and a rotor.
Okay, and then you've got a shaft that runs through, and then there's kind of like a gear mechanism that runs into this casing. Is that right?
There's a pinion at the end of the motor. The pinion goes to a gear. The gear goes to the gear case wheel, and obviously to the what we call the suspension tube or cannon tube on the axle.
Okay, so a bit like an electric car these days. Actually, what happens is that the power's modified by varying the ampage that's coming down here from the generator, and that speeds up the motor, which speeds up the wheel, and off we go.
That's correct.
So unlike a car, there's not gearing in the same way, is there?
No, there isn't. No, and the gearing, Ralph, really is done by the load demand module, because you obviously have to, depending what the load is behind the locomotive, will depend on how much power the driver needs to give to the engine in order to ramp up the revs.
Okay, so we're kind of seeing the back end of a diesel electric loco here, aren't we? Well, we've got the engine, the alternator, big fat cables coming down to the traction motor spinning and connecting to the wheels, and the wheels on the right train go round and round. I think there could be a song there, couldn't there? Okay. Do you want the next slide, Bob?
Yes, please. So then, of course, we have an electric locomotive, and we are in the decarbonisation era, and electric is the future. Here we have 25 kV, which is overhead, compared to 750 volt DC, which is third rail. In the terms of this particular locomotive, we have an overhead pantograph, collects from 25 kV provided from the network rail substations. This electricity goes down into the transformer. The transformer then forms through the main rectifier through a DC link. So you have an inverter. This controls the amount of current going into the traction part of the locomotive. So instead of having a diesel engine, you're essentially taking the electricity direct from the cable, and you've got rid of the diesel engine.
So actually, I always think of electric locomotives almost as portable transformers.
They are.
Yeah.
They absolutely are. And in many cases, and you'll see this in this drawing where it says three-phase AC motors. Again, you have AC drive, so you have much better torque availability, which is why a lot of AC locomotives are what we call bobos, not cocos, i.e. they have 4 axles, not 6 axles, but they still suffer from, although good tractive effort, lower tractive effort, because they haven't got the adhesion to the rail of the weight. And TE tractive effort is all not just about power, but it's about weight distribution.
So using the same nomenclature we were using before, Bob, where we had diesel electric before, effectively we've got electric here, and so we just call it an electric. And
yes,
yeah,
absolutely. But you've still got motors on the axles.
Yeah.
And you've still got the cables going up to a form of generation. But that generation has taken part in a power station, either Radcliffe or somewhere else in the country, and you're sending the electricity down the cables.
So does that mean that electric locos are often a little bit lighter, Bob? Is the transformer, presumably because the transformer weighs a bit less?
Yes, so electric locomotives do tend to be a bit lighter, you're absolutely right. But electric locos tend to be AC drive, so they have a much better torque to the rail on the motors. So they're much more controllable than an older DC generator drive diesel engine.
Okay, and I think we might come back to this when Neil's talking, because weight's quite an important point when you're overcoming friction, isn't it? And so with electric locos, because they're a little bit lighter, there's a little bit of a problem there sometimes.
Immensely important. So when we get to the last slide in my batch, I'll show you a locomotive that GB Rail Freight has got now, which gets over that problem.
Cool beans. Okay. Wow.
So
look at
this is an old picture that actually came out of a long-time British Rail document. It shows a Western Class 52, and I just wanted to point out to you really all the shafts. So there's no traction motors here whatsoever. You've got an engine with a shaft driving to a hydraulic transmission. That's a 3-stage torque converter transmission, very similar to what you have in your car.
Is that this bit here that I'm trying to circle?
There.
Yeah. Okay.
Yep. That's about 6 tons of weight. Wow. 3 torque converters full of oil whizzing around. The shaft rotates at engine speed. The engine speed is then geared through the torque converters 3-stage until you get to 1-to-1. You then have another shaft which goes to what we call an intermediate gearbox.
Is that this?
The intermediate that's number 2. The intermediate gearbox then goes down to the bogie, and you have 3 axle gear cases, which again are shaft driven from the intermediate gearbox. So this is diesel hydraulic. You have no generator, no alternator, no traction motors, very, very simple mechanical drive through shafts and gear wheels, direct drive from an engine.
Okay. So we call this a hydraulic locomotive, and it's a hydraulic mechanical locomotive in some ways, in that it's got a mechanical transmission.
It's got a hydraulic transmission, but it's driven by shafts.
Driven by shafts, that's what I meant. Okay.
Yep.
Looks very similar to the arrangement on steam engine almost, Bob, with all these.
Yeah, it's quite an old arrangement, and actually it's very much still in vogue around the world in many cases. You might be interested to know that a lot of the DMUs we run today, like 170s, Turbo Stars, 158s, are all based on this principle. They have a shaft to avoid transmission, which is shaft driven to an intermediate gearbox, exactly the same as this.
And why do they do that? What are the advantages of the hydraulic transmission, Bob?
First of all, it's simplicity. So in this particular case, the workshops on the Western region were busy with steam engines until very late. So they wanted something very simple. They didn't want to put electrics into the depots. They wanted something that was relatively simple to maintain. The second thing is they have a lot of grunt force. So the hydraulic transmission is tremendously powerful. This loco had an attractive effort of over 72,000 pounds at the wheel, which is why it used to power the Foster Yeoman stone trains out of Westbury, for example, as well as express passenger trains. Immensely powerful at very low speeds.
And how does that compare, Bob? I mean, that number doesn't mean too much, but compare it to a modern locomotive of 66. I mean, how would you compare with that?
Equal.
Equal, yeah.
Yeah. But this loco had 2 high-speed revving engines and 2 transmissions, so it was almost 2 engines bolted together back to back.
Right. Okay. Well, very interesting. Thank you.
If you go to the next one.
Ooh.
So there you go. This shows it in more detail. You've got 2 engines, shafts, which are number 3. The shaft goes to the block number 2, the transmission, and then you have all the shafts going down to the bogies. It looks complicated, but actually it's very, very easy. The difficulty is actually getting to all the shafts and the components. But in terms of actual longevity and ease of operation, they were ideal. The problem is that long-term in speed, for example, hydraulic transmission drops off at the higher speed curves. So they don't tend to do more than about 90 miles an hour because of the design of the torque converter allows for much better grip and torque at low speed rather than high speed. And they tend to be very complicated in terms of using 2 engines to get the necessary power ratio to the transmissions rather than 1 big engine to a generator.
Okay. Interesting to see how these things have evolved. And talking of
So-
evolution,
And then, of course, you get to the modern day locomotive. I admit this is my baby, so I have to admit to a certain amount of soft spot for this one. But this is my Class 99, which GB Rail Freight have ordered. This is a bi-mode locomotive, so this is what we know as the best of both worlds. This is a heavy freight Coco loco with a 2,500 horsepower diesel engine connected to an alternator. And it's also a 25 kV electric loco with a 7,150 horsepower converter and transformer. So this is a bi-mode locomotive. It allows you to go 25 kV on all the wires in the UK. And then when you're not under the wires, it has a diesel engine, which is capable of running at line speed and hauling your train to the sectional times. And this is AC drive. So you have the same AC traction motors, very modern AC traction motors, very modern electronic control through load demand. And this is all done for whether the electricity comes from 25 kV through the transformer, or whether it comes from the engine and the alternator and the transformer.
wow. So let's just unpick that a bit here, Bob. So this is the transformer. So this is the electrical bit.
Yes.
You said that was 7,000 horsepower.
7,150 horsepower.
And a 66 is about 3,600.
3,300. So that gives you some idea of where we're going.
Yeah, exactly that. So it's twice as powerful, and it's also got AC traction motors, which the 66s have got DC traction motors, haven't they?
That's correct. So
Yes.
these traction motors are half the size of a D43 on a 66,
Yeah.
and they're directly coupled via a what we call star coupling to the axles. So they're much more directly coupled, and they have much better control.
Okay. And unusually for an electric locomotive, you've gone for what you said, Coco, a 6-axle, 3
6-axle.
here and 3 here. And why have you done that, Bob?
So this is not only just to fit everything in. So we needed something which provided us with sufficient power. So therefore we needed a big locomotive to get the bigger engine in and also the bigger converter in. But actually it's about weight. So we needed sufficient weight to the rail head, the wheel to the rail head, enabled the TE to be very high, which will enable us to haul very heavy intermodal trains or aggregate trains throughout the UK. So that way we had a 6-axle loco, which gives us maximum tonnage of the loco weight to the rail.
And then you've got the diesel engine here, which you said was about 2/3 of that of a 66, which is more than sufficient to get the final mile and all that kind of stuff. Is that right?
Oh, well, it's more than enough. This is 1.864 megawatts, so over 2,500 horsepower. This is a main line that's more powerful than your average 47.
Yeah, okay. And you've got all the traction motors and all that kind of stuff. That's great, Bob. That's great. When are we going to see these?
The first one, August 24.
Wow.
If I deliver it on time, my trips to Spain.
Cool beans, cool beans. Bob, third rail pickup or not?
No, this particular loco doesn't have third rail. So third rail presents its own problems. As you know, the only 2 locos, the 73s and the 92s, operate on third rail. There are specific problems to third rail. Siemens have done a good job on the 700 series, where they're doing the 750 and overhead bi-mode on the Thames link for passenger trains. But diesel locos, it's particularly difficult in terms of current generation. So we haven't done 750 volt DC at this time.
Okay, well, thank you. So this really is the future, isn't it? Really, I mean, this is a bi-mode locomotive with a very powerful diesel engine. You're saying really is akin to having a mainline loco. It's 2 locos in one in many ways.
It's 2 locos in one. Yeah. And because of the modern equipment and material available, we've been able to scale it down. It's almost identical to the locos that are currently running in Germany, in France, South America, New Zealand, and Taiwan.
And Bob, it's being built by
Stadler in Spain.
Stadler in Spain. And Stadler are building a 4-axle version of this, which is the 93, isn't it? Although it's a little bit different.
It's a little bit different. It's a tri-mode. It has a very small engine on it and a booster pack batteries.
Yeah.
It's a very competent, very technically exciting locomotive, but it won't have the haulage power of a Class 99. It only has a very small engine, last mile engine, if you like. It's not a heavy freight loco.
Yeah. Okay. So that's why you've got So that's really, really interesting. So let's just summarize there. We've kind of been on a journey there. We've talked about the diesel power pack, the electric power pack, and the different transmissions that we've seen. So we've ended up with the state of the art, very, very exciting locomotive that we're going to see 2.5 years time. I've got that right. No, 18 months, Bob. Got it wrong.
Yep,
Took a
18
year
months.
off you. Okay. Well, great. Well, thank you for sharing that, Bob. That's really, really interesting. So there's a bit of an overview there of locomotives, and please, if you've got any questions for Bob, it's a unique opportunity to really go to the guru here, because Bob knows these things inside out, literally. So please put any questions you've got on the question and answer.
Yeah, so we've got 3 questions, and rather than store them at the end because they relate to Bob's bit of the, we've got one from Malcolm. In the diagram of the electric loco, nothing other than the transformer primary was connected to Earth. Is that right?
No, the loco is connected obviously through the wheels. So that you have wheels, axles, and a body shell, and the whole locomotive has to be earthed properly in order to not to give any auxiliary currents or voltages or DC frequencies through the rails to the signaling equipment. So the loco, in a sense, is isolated from everything else, and the transformer is heavily earthed.
Okay. The next one from Felix. What is the efficiency of 3 torque converters in the series? I presume that's the one when we're looking at the Western class.
So the efficiency at low speed is very high, but it drops off very quickly at higher speeds, because the oil itself becomes thinner, you become faster in speed. So the efficiency is actually reasonably low. It's probably about 60 to 70% at low speed, but drops off to about 40-50% at high speed, which is why the speed curve drops off.
Okay. And then finally, Mitch has asked, why did it take so long for AC to take over from DC?
Cost. That is the simple answer. DC is very, very simple. It's very easily controllable. AC has been more of a revolution in terms of electronic control and in terms of size of motors available. And so that's why it's a question of cost.
Great.
Okay, that's all for now. So let's carry on.
Okay, thanks, Bob. Okay, so over to Neil. Neil, away you go, mate.
So, I mean, I think one of the key questions is, what does this all mean for the industry? Which basically cares about, how big and heavy the trains are that they can move. And what Network Rail has is the sort of freight trading load books, and they cover sort of coupler strength and what you can do with the available tractive effort from the locomotive. And it gives you a simple output, which is the number of tons, the maximum number of tons your train can be. And then there's a third element, is how fast can you actually run the train? Can it keep to sensible timings on a constrained network? Quite often on constrained bits of the network, it's the timings that matter. And then in a number of cases, it's actually the sort of coupler strength and sort of T limitations that matter overall. Then there are a whole lot of non-train related or non-train engineering related constraints, which are all around sort of terminal and loop lengths, and just sort of physically a lot of terminal and track geometry.
So Neil, this is actually an extract, literally a current extract from the loads book, and the loads book is actually a series of Excel spreadsheets in this format, isn't it?
Yep.
Yeah.
Yep. Soon to be digitized and slightly more database searchable, etc. But at the moment, it's a spreadsheet that effectively is in printout format rather than actual spreadsheet format for electronic use.
And so, and we'll come to this on the right-hand side. We've got a series of coupling strengths. The 23 ton is very historic. 34.5 ton we see on a few of the intermodal wagons and a few of the older tank wagons, and then we've got our more normal 56 ton. So you can see here that from Victoria to Battersea, you can run with a much higher weight based on coupling strength.
Yeah.
But then,
so most of the time, you'd expect with the higher strength couplers, the limitation to be on the couplers, and it's actually quite hard for a locomotive to generate enough tractive effort to theoretically break the strongest couplers. It is possible, and with newer locomotive types, it becomes even more possible.
Yeah.
But most of the time, it's the grunt the locomotive's got and how well you can actually transfer the power to the wheel that makes the biggest difference.
And then what we've got
impacts the timings as well. And
what we've got down here are a series of locomotive classes, many of which have completely died, 58s, 31s, 33s, but they're still in the book for historic reasons. And basically, these aren't very powerful, but the more modern traction, normally the most powerful ones are the 60s. That's where we get the biggest numbers. So on this route from Factory Junction to Brixton Lane, you can run up to 3,105 tons, assuming you've got a 56-ton coupler. If you've got a 34.5-ton coupler, then your train weight is going down to 2,315. So that's the way it works, isn't it?
And just to sort of pick up on sort of Bob's point about sort of 3 axles and tuning things correctly, if you look at 66 and 67, virtually the same engine and traction electronics, but you've got a sort of 2-axle versus 3-axle per bogie difference, and also the sort of differences in gearing as well. You can see with the standard 75-mile-an-hour geared 66s, you then go down to a 65-mile-an-hour geared 166.6s, you get a bit more maximum tonnage there. But if you look at the 67s with just 2 axles, geared for 125 miles an hour, the amount they can haul is much, much lower.
Okay. And so in reality, operators, in terms of using the books, operators know where the steepest hills are, and therefore they can go to the loads book and work out where these are. But it's worth saying we have this principle of a 3-legged stool, that there's 3 constraints. So there's the coupler strength, tractive effort, and timings. So basically, the tractive effort, the locomotive's got to be strong enough. Coupler strength, the couplers got to be strong enough so they don't go pop when the engine plies it. And I think with Bob's new locomotive, that could be a problem. And with the 99, coupler strength will become more of an issue because we've got a lot more tractive effort. And finally, we've got to be able to go through the section fast enough to stop those old passenger trains moaning. So speed is an issue as well. Thanks, Neil. That's very helpful. So
looking at the sort of the first leg of the stool, the sort of coupler strength, there's an RSSB research project last year, 1256, actually looking at coupler ratings. There's 5 common types of screw couplers in use on freight wagons and locomotives in the UK. 2 of those coupler ratings had what you might call much larger reserve or safety factors than the other coupler types, and that led to lower ratings being used in the UK for those coupler types than in Europe, where they're successfully used with the slightly higher ratings. So that project looked at increasing the actual maximum load on those couplers slightly, and that sort of affects about 50% of the UK wagon fleet. So that can actually allow the sort of maximum train lengths to go up in some cases. The other part of the project looked at effectively refining the maths, which currently went back to the late 1960s. And for simplicity reasons, they assumed that the worst geographic constraint in terms of gradient or curvature applied to the full length of the train. In reality, that doesn't happen too often. There are cases like Shap and BTIC where it does, where you have extremely long gradients. A lot of other times is you've got, say, a short chord with extreme curvature, or you've got a very steep uphill, sort of very short section overall, typically round junctions, that only affects part of the train. And if you only assume that the actual real geography applies to the relevant proportion of the train rather than applying the worst bit to everything, you also get some improvement in the maximum trading load to the trains.
Okay,
that's
coming
going
out
through the processing industry at the moment.
Yeah, it is. And so actually what's one of the things that came out of 1256 was a definition of a new coupler strength, a 63-ton coupler, which isn't in the loads book at the moment. For those that are the most recent wagons that Greenbrier have built, and they've got a 1.5 meganewton European coupler fitted rather than the standard 56-ton UK coupler. So there's a few vehicles out there that are getting much stronger on that. I think we're not going to get any further increase in coupler strengths, because actually the wagons are going to start having the ends pulled off. But there's some really great news here. So, okay.
Yeah.
Thanks,
It's
Neil.
worth mentioning the coupler is deliberately designed to be the weak link, not anything on the wagon. So you break the cheapest bit rather than
This
the
bit here.
expensive bit.
Yeah,
Yep.
this little bit here that's easy to fix. Yeah.
Yeah. So the chain links are effectively designed to break before anything on the hook does.
Bit like a fuse, really, Neil.
Yep, exactly.
Yeah. Okay.
So sort of looking at sort of in terms of the tractive efforts, this sort of harks back to again in the couplers, sort of work from 1967 onwards in MT19, and the outputs were defined as tables for 3 different radiuses of curvature between what they described as very sharply curved, and straight, and for a whole series of uphill gradients on the grounds that that was going to be limiting, on the grounds that it wasn't going to be downhill gradient limited. The calculations mostly last run in 1986, and then sort of prototype off the drawing board for class 60 run in 1989, and that was the last time the code was run. And sort of Fortran 4, the codes got lost. The IBM 360 it ran on got binned, and there's also there's no documentation apart from effectively the input assumptions and the output tables. So recently we've actually been doing an RSSB project reassembling what the actual assumptions were and how the calculations were done, and how you can actually make this work for new locomotives. So for example, one thing we have coming up is that, say, for example, Bob's class 99 is that can produce a lot more tractive effort than you can actually get adhesion quite often, say autumn. So you've got to make assumptions around maximum adhesion in practice, whereas the performance of the late 1960s BR locomotives was comparatively so much worse that you didn't really have to worry about that, because it was limited by the performance of the locomotive, not the adhesion you could get.
So these numbers here, Neil, are the basis of what we see in the
load books. Yeah, so it's
what
maximum tons of wagons behind the locomotive.
Yeah, so what they will do is they will look at this thing and they will look at what the ruling grade is, and then they will go to the table and they will find the number that applies to this and apply it over the whole train.
Yep.
So basically what we're saying is that our current loads book 2023 is based on this document here. Okay.
And it's conservative based on conservative. So what we've done is just sort of really simplifying what the mechanics of the original model were. They're sort of effectively 4 components to the resistance, sort of effectively gradient, acceleration, on the grounds that it was mostly concerned with lower speeds, and you actually need to be able to start off and then keep accelerating and moving slowly. So you put a little bit of margin there. You're not interested in the net force being 0 to move it. The tractive effort has always got to be something slightly higher than all the other resistances put together. The mechanical resistances, so all the internal resistances to do with the wheels and the aerodynamics from within the train. And then the curving resistance is effectively extra effort to pull the trains round sharper and sharper corners as the wheel resistance goes up gradually there. Key thing on the tractive effort side of the equation on the left is sort of you've got at an adhesion limit, which is limited to sort of effectively a function of the weight on the axles and the actual friction you get at that point in time. And so effectively got an interplay there. The older rules, largely it was always, you got everything the locomotive could provide because you were so far away from the realities of friction on the network, whereas now you've got so much better force delivery at the wheel that your adhesion or your probability of getting adhesion is much more of an issue.
Yeah, so this looks like a bit of a scary thing, but in reality it's not so bad, is it? What we're saying is that the available power has got to be greater than the sum of the loco forces and the wagon forces, which are based on these things, getting up the hill, around the curves faster and overcoming the grist in the mill, so to speak, and so that makes sense. And I think what you're saying is there is a cap with adhesion, because if the adhesion's enough, you get wheel slip, and you actually just slipping and sliding all over the place. Yeah.
So for example, with electric locos is quite often they can be maybe a bit too light. So effectively adding a diesel engine in actually puts more weight on the axle. So it actually helps with the maximum tractive effort you can get out of them. So effectively, by adding more weight, you take down the adhesion value required to achieve the tractive effort overall.
So we've added some detail to this now, haven't we, Neil?
Yep. So effectively, just sort of to put things in context, it looked at sort of two cases starting out where resistance is slightly higher from friction in the bearings, and then a rolling cases overall. Biggest one is gradient. That's usually the real killer. And tight curvature, you only get really high resistance numbers there for tight curvature, which automatically limits your speed. So you can't, with the highest mechanical resistances, the highest aerodynamic loads, those occurs at high speed. So you can't have both mechanical and curving resistances high at the same time. So there's a sort of bit of an either or going on there. But the big killer is usually gradient, and then sort of aerodynamics at higher speed.
Okay, thank you. So this actually puts some numbers on here, and you can see that part of this research project, we're coming up with some quite complicated formula that for putting some mathematics behind this. So I guess what we're doing now, Neil, is recalculating those numbers. You talked about the Fortran logic that's been lost. Presumably this is backfilling that space, is it?
Yes, yep. So we've effectively backfilled what's there. There are then a whole load of questions about input assumptions and relevance of those still. And BR, through the years, certainly in the 70s, they did 2 tweaks, and they certainly did. We can see they did 1 tweak to what was going on in the 1980s, and they had an entire report with a follow-up report saying this is what we need to do to sort things, but they never actually fully implemented it by any stretch. They did pick the easy bits, did those changes, but left a lot outstanding. So that's some of what we're doing at the moment, is addressing the outstanding issues that they identified but never addressed.
Thank you.
So going back to sort of one of Bob's earlier points is effectively, well, we've got a limitation, which is effectively on diesel engines, you're limited by the engine power because of the loading gauge and the axle loadings with the maximum engine weight. So what we want to do is try and get more out. And we sort of effectively define that in terms of force or torque at the wheel from the available input energy. Sort of got a nominal efficiency versus speed curve for a DC traction motor. There's on the main bit of the curve, there's a sort of a sweet spot, and there's a bit of curve there. So there's a lot of the locomotive gearing goes into thinking about how optimizing that sweet spot and effectively not having the tail off at the higher speed end. And then there's a sort of pretty much straight bit on the left-hand side where you've got the adhesion limit of the locomotive and the sort of very poor low-speed motor torque of a lot of the DC traction motors comes into play. The bit on the left means if you stay down in that bit of the curve, all the traction electronics get rather hot and they lose efficiency even further, which is really quite bad. And that comes into what's defined as the continuous ratings for the locomotives, is when they get traction electronics get so hot they degrade to a low performance. And that's actually one of the criteria on the network, is to gauge that. But effectively with the newer traction electronics, that's no longer relevant because you can no longer get the electronics hot enough to degrade the efficiency enough to limit the performance. So when we look at sort of modern 3-phase drive AC systems, you actually get a much flatter torque curve for most of the right-hand side. That makes it far easier to actually work out for the computer systems to actually deliver what the driver wants. And the curve is higher up, which means more of what you try and put in gets delivered to the wheels. And that's a lot better overall. That means you can haul more. And also on the left, the point where you go from that straightish line to the curve, that's moved further up and to the left. So that's all good for better low speed performance and efficiency. And that helps with effectively, getting the electronics less hot. And, typically DC systems probably in about 75%-ish efficiency overall. Whereas you look at some of the AC systems overall, you're looking at about sort of 90% efficiency overall. So there's a useful thing there. And you're getting that better efficiency over a much wider range of speeds as well, not just the sort of optimum case.
So this is reinforcing the point that Bob was making about how AC traction motor delivers more power.
Yeah.
And not only does it deliver more power, but interestingly, freight trains aren't often up here. They're normally going quite slowly.
Yeah.
And so actually we're getting a lot more power at the slow speed.
And that also helps in the reverse case where you've got regenerative braking. Regenerative braking can be much more efficient compared with potential older systems, whereas on anything with DC, it was very horrifically inefficient. Just sort of linking to Bob's earlier point is that motors on the 99 are far lighter. Is typically with an AC traction motor of for virtually the same characteristics, the motor will spin about 50% faster. So you can and that leads to sort of nominally 50% more power you can get out of it, but then you adjust the system round to actually sort of compensate for that. And what you say is, well, do you want 50% more power out of the motor? Well, possibly not, but you can actually go far lighter, far smaller and lighter motors, which are then easier to cool and you get better performance out of.
Okay, thank you.
And you also get naturally very good wheel slip protection in there.
Yeah, which is important.
So
the third leg of the stool is about timings.
Yep. So on heavily constrained bits of the network, which applies to probably sort of somewhere about half of the freight overall, is timings matter. But people automatically, when they say timings, people think of speed. What you actually need to think of is pace, which is effectively time per unit distance. So in the rail sense is sort of effectively seconds or minutes per mile, because that's the way the sectional running times work and that's the way the timetables work. It's all about pace, it's not about speed.
So the sectional running time, Neil, says that you've got 90 seconds to get from Battersea Junction to wherever it is. So the sectional running time, the section is a section of track, and the running time is the time that you've got, the maximum time you can be in there before theoretically you're causing delay to the train behind. Is that right?
Yep, and it's in 30-second increments.
Yeah.
And sometimes fudged a little bit around the edges. So effectively nudging those times down even a couple of seconds over a number of sequential segments can actually really help. And going back to the sort of, Ralph, what you said about sort of, the trains are operating often a lot lower down in speed, is the pace, the increments in pace have a far bigger change at lower speeds. So effectively you can improve what you're doing at under 50 miles an hour, has a much bigger impact on freight trains than at higher speeds. If you look at the third column on the right, it's for every 10 miles an hour increase in speed you go, how many seconds per mile difference it is versus the lower increment. So going from 80 to 90, you're only seeing sort of 5 seconds per mile difference in speed, whereas going from 10 to 20 miles an hour, that's 3 minutes.
Yeah, thank you.
So yeah, targeting sort of low and medium speed performance of the train or the track. So low speed points and loops, they're all really bad as well. Weak bridges, effectively, if we can sort the low speed limits, that has a huge impact on freight overall. And sort of effectively linking back to what does this do with TE? So say going from an older midlife diesel locomotive with DC, so it's effectively the black curve, to something newer, effectively with green curve, is you see a sort of, maybe around 20% difference at the low speeds on the flat bit of the curve on the left. So you can haul proportionately more train as you would expect, because there's not much aerodynamic influence that thing at those low speeds. You start taking the speed up, the difference in deliverable tractive effort then goes up hugely. So you're actually looking at more than 100% increase in tractive effort as the speed picks up to say beyond 25 miles an hour, up to sort of the full sort of 75 mile an hour max for most freight. So that means you can do hugely better timings for those ones, and the ability to get paths where they don't currently exist should be better.
So Bob has given us the traction curves for the 99s, and we're going to put them into the model that we showed earlier. And I think that one of the benefits of the 99s is not only will they be able to pull longer trains, but they're able to do it a lot faster. So that's a big deal. Thanks, Neil. I think that's the end of your section. Is there anything else that you wanted to cover off?
No, I think that's any questions.
Okay, I think we've just got a second, Bob. But just any comments on Neil's anything you'd like to say to add to that that people might find interesting?
I think it was extremely interesting and very comprehensive. So thank you very much, Neil. And really, there Neil's confirming the benefits of AC traction over earlier DC traction, and confirming the fact that weight is everything. It's you know, at the end of the day, you can't get away from the fact that there is a calculation that provides you to the railhead to the wheel, which is weight and the gradient and the load and everything else. And Neil's very well explained that. And I think it goes to show that we're all moving in the right direction in terms of motive power.
Yeah. Thanks, Bob. I think, Phil, we are done, and
Great.
I'll hand back over to you for questions.
Thanks a lot. Yes, we've got a few questions. So going back to the tables that you showed, which the limitations of train length and weight. There was a question from someone who said, where can I access this information without asking Network Rail every time I need route data? So I think you mentioned at the time that the intention is to digitize all of this stuff. Is it going to be something that is more widely available?
Well, the first thing is that it is Network Rail data. So, but Network Rail are very generous in sharing their data. I think all the freight operating companies have got access to the loads book. I think if you wanted to get hold of a loads book, if you asked somebody at Network Rail, they probably, it's not secret information, although it's not widely available. So I think that's the first thing to say. The second thing
I think it's finding the people with the spreadsheets is usually the issue.
Yes, but certainly most of the route freight managers, if you contacted them, I know Mark Bridell and many of the others have got access to them, and so they would be able to share them. But it is their proprietary data. Yes, Network Rail are planning to digitise this. If you compared this with some of the European infrastructure managers, it is a bit antiquated. They've got digital systems where you can say, well, I want to go from Rotterdam to Lucerne, and it'll just tell you what the constraint is, and you kind of have to need to know the worst situation.
So DB is probably the best overall,
yeah,
and most accessible. Some of the others can be a bit hidden as well, even though they do exist.
And so I know that Network Rail, we've been talking to them about how we get the benefits out of 1302, and I know that they're coming out for a tender to actually start to digitise the freight books. But I think that's probably going to be, I have no idea how long it'll be, but I imagine it's a year or two before that actually happens. So for the time being, we're on Excel spreadsheets.
Okay, great. So the next one is from Malcolm. How do features such as creep control and sanding impact on adhesion?
Both help massively. The idea is normally you wouldn't want or need to use sanding, but obviously when the railhead gets wet or you've got curvature, so you've got more slip on the outside wheel going around the corner, then you do actually sort of need sanding. In terms of sort of creep control or wheel slip protection, everything like that, the actual inherent features of the AC traction motors is that you need to supply them with a frequency that is just very slightly faster than you want the motor to rotate. And if the frequency is very slightly out, the torque from the motor falls off rapidly. So effectively the natural electrical control systems built in effectively do a very good for first order creep protection system. And effectively what you're also looking to do is you need to generate the adhesion, you need a tiny little bit of slippage on the wheel. So the digital sensors on the modern locomotives and even sort of all the passenger EMUs are actually sort of targeting the sort of magic 1.5% slip with slightly more slip in the wet to generate the maximum adhesion levels. So it's actually one of the bits with AC is you can actually improve the probability of getting high adhesion just through the electronics it's got there. And then you do sort of all your more sophisticated wheel slip protection as a sort of second order bit of logic rather than a sort of first order on the older locomotives like the 66s.
Okay, thanks. There's a couple of things that occurred to me while we were going through this. So having had a little look, as one does on the internet, about diesel electric, I believe in the early days of diesel electric, we had the sort of model where there was a diesel engine driving a generator, driving the motors. And then things get a bit more sophisticated when we introduce things like rectifiers and inverters between the engine and the motor. Now, I know that regenerative braking is something which is more applicable to DC electric trains rather than diesel, and it's probably easier than in that environment for DC than AC. But I just wonder, looking to the future, if we wanted to recharge a battery on board our train for last mile performance on one of these hybrid type of locos, which is the better system to have for charging any onboard battery?
AC systems, because effectively what you do is even if you've got AC coming in at sort of 25 kV and 50 hertz, you convert it to drop the voltage down, convert it to DC, and then for when people say the three-phase AC traction motors, they're variable speed, they're variable voltage and variable frequency. So traditional electric motors, they're just effectively, they run at, you're putting 50 hertz AC into them. And that is very difficult to control the speed. And you need then effectively to say we're doing something different. And effectively what you do is use between about 0 and 70 hertz frequency to control the motor speed. And that drives a lot of the inherent efficiency. And going back to Mitch's earlier question, is you need basically the ability to create from DC an AC waveform of the voltage and frequency you want quickly is basically the electronics limitation. And then it comes as the cost of doing those electronics as a technology wave. And then there's a cost wave, which comes after that is when that comes down. Because you've got effectively a DC stage in there, which is not too dissimilar to third rail DC in terms of sort of voltage and that's then very easy to actually charge batteries off that stage.
Oh, great. Okay. The other thing we just don't quite understand, I'm sure it's obvious to everybody else, but what is the relationship between tractive effort and horsepower? Well, in the past, one used tractive effort as one's sort of assessment of how powerful something was, and we hear horsepower referred to much more often these days. Is there a direct relationship, or is it a bit more complicated?
There's a sort of direct relationship. So it's effectively the tractive effort is sort of power divided by speed with an efficiency, speed dependent efficiency factor thrown in. And that speed dependent efficiency factor looks roughly like what I was showing on those two DC and AC motor charts.
But also, isn't it, actually horsepower is more about how many horses you've got on the engine, and tractive effort is about the force you're applying at the railhead.
At a given speed.
Yeah, I find that a much more useful way of doing it. I mean, actually, how big your engine is great, but actually the size of your traction motors is just as important, and nobody really takes that on board. And so, you know, actually it's just not just the engine, how many horses you've got, but it's actually how those horses are fed and watered so that their power goes down to the railhead, and that therefore you need to consider the transmission system and the losses and how it's converted. So when we talk about TE, tractive effort, it's the torque, the horizontal force that's applied at the railhead.
Yeah, I mean, it's also worth mentioning on the efficiency point is the auxiliaries on the locomotives are getting much more efficient as well. So instead of something like a 66 where you've got 2 alternators and then a generator for some low speed electrical supplies, you've got 3 different electrical systems on it. Is the newer locomotives, you have a single alternator, and then you worry about converting the voltages for use elsewhere later. And again, 66, you've got a mechanically powered air compressor that rotates all the time with a bypass valve when you want the compressor on and off, but it's still rotating at the engine RPM, even if you're not actually looking to sort of build up air reserves. Whereas the newer locomotives, you've got electrically powered compressors, which are only on to match your air demand.
So Phil, I think what we're saying is that actually it's important to consider the whole system of the train. What Neil's just articulated, the kind of the internal losses, where we're losing power to go and do stuff domestically on the locomotive. So, you know, actually, it's great to have a massive, great engine, but Bob's thought very carefully about making sure that it's got 6 axles and AC traction motors so that you can put that power down. Is that about right, Bob?
That's correct, absolutely correct. And as you quite rightly say, it's all very well having a big engine, but you've got to be able to put it to the railhead, and that's all about AC drive, AC traction, and how we develop the relationship between the load behind and the gradient and the power available to you, as Neil has said quite correctly.
I just perhaps bring to people's attention that there's a company called Associated Rewinds in Dublin.
There is indeed.
Yeah. Who are just the most remarkable organisation that actually refurbish all of the traction motors. And, you know, people may not have been very exposed to traction motors before this webinar, but actually it's worth looking at their website, because actually through their website you can see what traction motors look like over and above our photograph, which isn't particularly helpful because it's all within the casing. But actually one of their photographs shows banks of people literally physically rewinding the copper cabling around the armatures. It's an old craft industry, and it's very, very interesting, and it's something that's not immediately apparent. So that's Associated Rewinds in Dublin.
Don't forget, Ralph, that the size of those motors has gone down. So, you know, we did have huge, big DC motors. We've now got much smaller AC motors, which develop more torque and are more controllable.
Yes, thanks, Bob. Because I'm really thinking about 66 rewinds that I saw. So yes, absolutely.
And the need to rewind anything on the AC side or rebuild them is sort of several factors, orders of magnitude lower, because you don't have sort of carbon brushes and flashover problems, and the thermal management's far better. So they may be getting less business in the future with AC traction motor rewinds needing being once in a blue moon.
You don't have commutators and carbon brushes, Ralph. It's AC drive, so you have a much cleaner motor, no carbon deposits, much less risk of ionization and flashover.
Big words.
Thank you for that. Just perhaps a reminder that we don't really encourage commercial breaks on these webinars, but I'm sure the company you referred to is doing a good job.
The rewinders are available.
Yeah, exactly. I think we're sort of coming up to time now. There's a few requests for information that's come in, which I will cover in my closing remarks. But one or two people are having to start to leave now. So we've had a sort of farewell wave from Malcolm, who says every day is a learning day. Thank you for this presentation. Very informative. So I think that's certainly well worth us doing. Now, thanks to the 3 of you, Ralph, Bob and Neil. Now, don't forget that if you would like a copy of the slides, please let Yvonne know via our website, and we can get those to you. We have had a request from someone from Birmingham University, and as I said at the beginning, this webinar has been recorded, and you can obtain a copy of the recording. And what you do with that obviously is then up to you. So that was a request that came in. So just a reminder then, we've got some more events coming up. Next Tuesday on the 7th of March, Ralph takes a break while we host a webinar in association with binary carbon, looking at problems or the challenges presented by the circular economy, and that's part of Binary Carbon's Decarbonising Transport Week. Just a reminder that the third in these series of technical webinars is on Thursday the 18th of April, again at 8:30, and we'll be looking at rail loading and track access charging. And then the last in the series is on the 18th of May, where Ralph and his guests will be leading us through the intricacies of railway signalling. In the meantime, the Rail Freight Group will be holding their annual Scottish conference on the 29th of March, and full day details of that are available on our website, www.rfg.org.uk. And on the 23rd and 24th of May, we're holding our members' spring meeting in Southampton. So if you are an RFG member, would like to come along, those are the dates. And again, that's all on the website. And also on our website, you'll find details of our popular awards evening. And although that's not until September the 7th, entries for awards are open. So we look forward to receiving your entries. So from me, can I just say thank you for everyone for joining us, and we look forward to seeing you again soon.